This lecture deals with projectile motion, specifically looking at how projectile motion is a combination of two one-dimensional motions. So projectile motion is basically motion where an object is thrown from some angle or released from a top of a building where it moves off horizontally. And when it's moving through the air, it's moving only under the influence of gravity. So there can't be anything that's propelling it forward, and there's no air resistance. So it turns out that when an object is thrown at some angle or released off of the top of some surface, that the only thing that's acting on it is gravity, and gravity always acts vertically downward. So if gravity wasn't present and you toss an object, that object would basically travel in a straight line. So if you were out in space and you threw an object, it would just continue to move in a straight line forever and ever because there's no gravitational pull, assuming that you're not near any planets. With gravity present, that same object, when it's tossed at an angle, actually follows a curved path. And so we're all familiar with this because if you've watched basketball or football or soccer, basically any sport that involves a ball, when the ball is moving through the air after it has been set into motion, it follows a trajectory that has a curve to it. So it turns out that projectile motion can be examined by just looking at the combination of horizontal motion that doesn't have any acceleration associated with it, and then adding to that vertical motion where there is the influence of gravity acting downward. And so we've basically looked at horizontal motion in the past, where you have an object that's traveling along a straight line and it doesn't have any acceleration, so it's going to have the same speed at any instant in time horizontally and therefore cover the same distance every second. Versus vertical motion, so if you throw an object up in the air, it slows down on the way up and covers less distance every second, versus if you drop an object, it speeds up on the way down and covers more distance every second. So these two motions, the horizontal and the vertical motion, are actually independent of one another for projectile motion, and so we can look at them separately and then combine the motions together to see how a projectile will move. So if we start to just review projectile motion in terms of two one-dimensional motions, we can look at what happens along the horizontal direction. So as I just mentioned, if there's no acceleration, then a ball that's rolled across the surface would just follow a straight line path. And if the velocity is constant, meaning there's no acceleration, the object covers the same distance every second that goes by. So here in the animation, what's going to be animated as I click on it, I have a ball and it's traveling with some velocity v off the edge of a table. So in this case, the motion, if gravity was not present, the ball every second would just follow a straight line path. And it would cover the same distance every second that goes by. On the other hand, if you look at vertical motion and you have an object and you release it, so I have a hand up here and then I'm going to release that object, as it falls, it speeds up, it covers more distance every second. And so if I did the same thing here where there's motion with gravity present, but there's no horizontal velocity, it's just released, we can look at how the object would continue to increase speed and would cover more distance. And we know the distance covered over time, that depends on time, the distance is just 1/2 the gravitational acceleration, which is 10 meters per second squared, at times the time squared. And as we mentioned before, we know the velocity as it's falling down increases 10 meters per second every second. So it turns out that projectile motion is just a combination of these two one-dimensional motions, the motion in the horizontal and the vertical direction. So we look at the horizontal direction where the object would be if gravity wasn't present, and then we look at where the object would be when gravity is present. So I'm going to just animate the picture. So here's my ball. It's rolling off the edge. It gets to the edge. 1 second later, if gravity wasn't present, the ball would keep traveling in that straight line path. If there was no horizontal velocity, the ball would just drop down here. So if I combine those two motions together, the object is actually located in the position shown here. And I can continue to do that. So after another second that goes by, the ball travels some distance and it falls down further than it did the first second. If I combine those two motions, my object is here, and I can just continue to do that. So basically, I'm combining horizontal motion with constant velocity covering the same distance every second with motion in the vertical where the object increases distance every second as it falls. So if I take away those two independent horizontal and vertical motions, I get the actual motion of the projectile, which has a curve associated with it. The big thing is that the horizontal and the vertical motions are completely independent of one another. Horizontal motion, the speed, the velocity is constant. Object covers the same distance every second, and in the vertical, the velocity either increases or decreases by 10 meters per second every second, depending on whether it's traveling downward or upward, and it covers a different amount of distance every second. So let's look at, again, this motion with gravity present and see what our velocity looks like. So in this case, I have that same object. It has a velocity in the horizontal direction on the table of 20 meters per second. So it covers the same distance every second. So as it leaves the edge of the table, at time t equal to 0, the speed of this projectile is along, or the velocity is along the horizontal direction, and it's 20 meters per second. 1 second later, the object has fallen off of that straight line path. Notice that the horizontal velocity is still 20 meters per second, but the velocity along the vertical direction is now negative 10 meters per second because 1 second has gone by, and the velocity in the y direction increases by 10 meters per second every second. After 2 seconds, again, horizontal velocity is still 20, but the velocity in the vertical direction is now negative 20. It's increased by another 10 meters per second. After 3 seconds, velocity in the horizontal is still constant. Velocity in the vertical has increased by another 10. And then finally, in this case, just before it hits the ground, the velocity is increased by another factor of 10 in the vertical, but still has stayed the same in the horizontal. So that's how we get that projectile motion and why the object, in this case, as it's falling, covers more distance every second that goes by. So first interval is a small amount of time, and so on. And the distance that it falls, we could figure out, again, by just looking at the distance is 1/2 gravity times the time squared. So if I wanted to know how high this table was, I know it took 4 seconds to get to the bottom, so I could use the fact that that distance from here to here is 1/2 10 meters per second squared, that's gravity, multiplied by that time of 4 seconds squared. So just as a really quick review, one of the big things about this presentation is that the horizontal and the vertical motions are independent of one another and that they can be examined separately. So everything we learned about horizontal motion with no acceleration is still valid, and everything we learned about vertical acceleration, vertical motion with the acceleration due to gravity, we also can use here. Let's consider this question. 2 objects start at the same height. Object 1 is released, so it's just dropped, and the object 2 is launched horizontally. Which object reaches the ground first? So if I go back to this picture, the idea is I have one object that's rolling off the edge and I have another object. At this same instant in time, an object is dropped. And you can watch a YouTube video that demonstrates this, but this animation, which is running very quickly, also demonstrates the idea. So I have this object, one is shot off, one is dropped, and the dotted lines here show you that those objects are falling the same distance every second that goes by because their motion in the horizontal is the same. This object is essentially has no y velocity to start with, no vertical velocity, so they both fall at the same rate. Now the one on the right has horizontal velocity, so it's going to be projected off at some angle. But they still reach the ground at the same time. But you can watch the YouTube video. I'm not going to pull that up here, and you can see the actual demonstration done. Here's another picture of, and this is going to repeat itself, but this is another picture of how the motions are independent of one another. So the airplane is dropping a package. So as the plane is traveling forward, the package has an initial velocity that's the same as the plane. So the arrows for the plane velocity and the horizontal velocity of the package stay the same. So they continue to line up with one another in terms of how much distance is covered horizontally, and that's why the package just stays underneath the airplane. If the airplane dropped the package and then accelerated, then the package would actually be behind the plane instead of right alongside it.